Hey class, so we're going to go ahead and start with the review of value iteration so that we can make sure we understand this before going into our midterm, as well as corrections for problem set 6 if you hadn't made any issues the first time. So let's go ahead and review the concept initially. So first we start with random initial values. So these are state values. For example, an example we've done in class, we always start with like 0, but you could start with arbitrarily any value. And basically, we're applying this iterative update to the Bellman optimality equation. And remember, we compare it to the expectation equations, which we used in problem set 5, where we gave you these state values for each state, and you're basically validating them using this equation. And what you see here, what we're doing is we're actually going through every single action and summing all actions given to us by our policy and the action values of those actions from the current state. Whereas what we're doing here with the Bellman optimality equation is we're not summing through all actions, but we're going to look at the values given to us by this function for all possible actions we can take from our current state. And we are picking the best one. So we're not doing any summation, we're just picking the best one. And that is a problem that I've seen in a couple of the problem sets I've seen submitted so far, in which people are summing like we did with the Bellman expectation equation instead of taking the maximum. So just if I were to explain this equation simply, it would basically be that for all possible actions, you go through a single action A, you look at the immediate reward you get for that action plus the discounted look at all the successor states that you can end up at from taking your current action A, and seeing the value of those successor states weighted by the probability that you'll end up in that successor state taking your current action A from your current state. So we're going to keep applying this, and really it's important to remember that this is basically done in iterations. So there are no intermediate values in the sense that you don't use the next iteration of the current state of that value until you've updated every single state already in the previous iteration. And that'll make a lot more sense when we go through the example. So let's go ahead and go through the example we went through in class. So we're starting with a environment where you get -1 for every single action, with the exception being this gray spot right here, this gray state. And the way we're going to reference states in this video is it's the state 1, 2, 3, 4, all the way downwards. So looking at this simply, I'll just go through a few iterations until we get the point. So starting off, let's look at any state. So first, important to know that gamma is 1 and that your actions are moving up, down, left, or right, and if you move in any direction, you have a 100% chance of moving in that direction. So if I say I'm here and I move right, I have a 100% chance of actually going right. In this case, so let's say I want to calculate the value. So I initially started with these random 0 values. Let's say I want to calculate the value of this state right here. So calculating the value of this state involves what? So this is 1, 2, 3, 4. V of 7. So V of 7, what that's going to be is looking at all actions I can take from that state. So I can either go up from V7. So if I go up from V7, what happens? My immediate reward right here is going to be -1 plus gamma is 1. Probability that I'll end up, and basically looking at all successor states I can end up in. So if I go up, there's only one successor state I can end up in because of this rule right here. So that's just this guy. So if that's all I can end up in, that's all I really have to account for. So it's just 1 is the gamma, 1 is the probability, times what? Times the value of that state, which is 0. So it ended up just being -1. And you can see also as well as intuitively, everything in this example is surrounded by zeros. So if these values aren't really changing right now, so if the up case was 0, then the down case also the same idea. It's -1 reward for every action, and then we're going to go through all surrounding states you can end up in, and they're all just going to be one single state because of the probability of going to another state by taking that action is 100%, and they're all zeros. So really, you're going to get the same kind of deal, basically like this. And for now, I'm just going to ignore writing gamma anymore because we get that it's 1. 1 times 0 and also -1. So you'll see, like, basically in the next iteration, everything just becomes -1. So we're taking the maximum essentially of like -1, -1, -1, -1, and which is just going to be -1. So since everything is this -1 value, so kind of apply that here. This is the next iteration, which makes sense. And 0 itself is going to stay the same because it's just a terminal state. It's not changing. It's kind of, once you're in there, you're done. You don't need to worry about it anymore. Your reward after that, after being here, is 0 because you're done. So let's think about the next iteration now. Now this is where things get a little interesting, and we actually can use this maximum concept. So looking at, let's say, this guy right here. Well, let's first look at the standard -1. So looking at -1. This is V7 again. So V7 before we calculated to be -1. So like a lot of the other ones. And now looking at this, do the same things before. We can look at what we have is go up, down, left, or right, but it's going to be a very similar case. To go up, the immediate reward is also -1 plus. Okay, again, the only state we can end up in from if we go up is also going to be this state right here. So probability of 1 times the value of that with -1, which would give up to -2. So that same idea is also going to apply to anything else that's surrounded by -1s, only by -1s. So we know that V7 is going to be a maximum of a bunch of -2, so it's going to be -2 itself. But there is two special states here that aren't only surrounded by -1s, and that is this state right here, so V2 and V5 right here. So V2 and V5 are interesting. So remember, we're taking maximums here. That's the important concept. So V of, let's say, this is a V of 2. So V of 2, we know, and well, there's this guy. So V of 2, we know what? We know that we want to take the maximum, and we can go through the same up, down, left, right action. So let's just up again. Up again is going to be the same things before. Same thing as we did for V7, -1 plus. You can either go, if you go up, what's going to happen is you're going to go back down here. And so that's going to give us a value of 0, so 1 times -1, also giving -2. But what if we went, and then same for anything else, but what if we went left? Now this is where it gets interesting. So -1 plus, the probability of ending up at any other state, of course, is 1 again. But what's different here is that I have a state where I can end up in that actually has a value greater than -1, which is 0. So I actually end up with -1. So if I'm maximizing over -2 and -1, I'm obviously going to prefer the -1. So in this case, I'm not summing all these up, possibly going up, the values be going up on the left. I'm just taking the best one. So I'm taking -1. So in the next iteration, these would stay as -1. So everything else becomes -2. -2, and so on and so forth. And you can kind of see that the change propagates backwards. So like these ones are the closest, and they're because they're closest, they have a higher action value. Oh, sorry, higher value state value. So you can kind of follow that, and closer as you see, it propagates backwards. I'm not going to go through all the other examples we did in class already. I just want to make sure that the concept of that we're applying the Bellman optimality equation, not the expectation equation that I saw in a couple of the homeworks, making sure that we understand the difference. that is explained in these slides here as well, and we do kind of derive them later. Let's see. Now, I hope that's I hope that's clear at least, kind of these steps, how to do that, and also the further iterations of this example are in the slides as well. So now I just want to go through a homework example. So, of course, PSET 6 we released already. So I want to go through this example, and this example should look very familiar to you because it's exactly the same example as the homework. So what I'm going to do is go through actually one of the homework questions, a part of it, and then I'll still leave the next part for you guys to do for corrections. And again, it's very important that you understand how to use this equation correctly. So looking at this, this is a little different from the previous example because now we have a stochastic environment. So here we have our nice Bell optimality equation again, and this is a linear environment where instead of having always 100% going to the direction, you have a 0.8 chance of going there and a 0.1 chance of going left or right relative to the current direction. So we've seen this kind of scenario before already. So let's jump into it. Let's see. So starting with this state right here. So this is V3. So for V3, you state 3, and these are like, I guess, iteration. I guess V1 sounds very confusing. So iteration 1, and we'll call it iteration 2. And it's basically going to be where we're starting, and then where the next iteration is going to be. So remember that we still go up, down, left, or right. So if we went up, what would happen? If we went up, it would be going the immediate reward in this case is 0. Gamma is 0.9, so it's not 1 this time. And the probability of any state we can end up in. So if we go, if we're trying to go up, we may actually end up going left or right. So up has a probability of going has the value of 0 because it's going to the same state. But the other ones have 0 also for going left. But if you go right, you have a chance of hitting a 1. So that's basically the same as just doing 0.9 times 0.1, which gives you 0.09. Why is it negative? Okay. So what if we tried going to the right? So if we tried going to the right, it should be pretty clear that that's probably the best thing to do because you are heading towards this nice green terminal state of 1. So you are doing a very similar thing. 0 and the gamma is 0.9, and what you're doing is this kind is 0.8 chance of you going and getting a 1 reward, but 1 chance of getting a 0 reward, and then 0.1 chance of getting a 0 reward. It's going either up or down. So that should get you 0.72, which is the maximum of both of those. Clearly is max of 0.72 and 0.09 clearly is 0.72. So you would pick that for our next iteration. So remember the point that I was trying to get across earlier is the fact that if I were to calculate now next for the same iteration this guy, and this calculation needed to use this state value, I would use this iteration, the current iteration's value, not the next iteration's value. I can only use the next iteration's value once I've already gone through every single state of the current iteration updated already. Then I can only use it. Otherwise, then you leave it for the next iteration. So one thing to consider, again, is the fact that we are taking the maximum value. So in this case, this would be 0.72. And now let's look at another example, and I've seen a lot of issues on the homework with this particular state right here. So it'd be 1, 2, 3, 4, 5, 6, 7. You have 7. With V7, the action we could probably take are we go up. If you go up, we get a reward of 0 plus the chance of either of actually going up is we still would end up in a 0 state, but also the chance of going to that -1 is still there. And remember that the black dot or the black box state is actually just a wall. So if I went left, it ends me out back where I am at the same state. So what it's going to give me is -0.09. So obviously that doesn't seem like a very good reward or value. So let's think about what if we went left? If we went left from here, we could just do 0 plus 0.9, and then think about what we can do in terms of states we end up in. So if we go left, we end up back at the current state. If we actually the 0.8 chance of actually going in that direction, or we go up, or left relative is up, and there's a 0, or down relative to up, which also is 0. So that's 0.1 0 plus 0.1 0. And this gives us 0 again. So then taking the maximum again, both of these gives us 0. So this should stay at 0, and the same kind of applies to all the other states here as well. So for the next iteration too, this is all you have. So if you went through this kind of equation for every single possible state in this from iteration 1 to iteration 2, you end up with this at this value, or this environment. So yeah, I hope that it kind of explains value iteration. In terms of like the most popular questions, like why do you care about this? I guess this slide kind of gives you the whole big deal about this. It's kind of extracting the optimal policy by regionally acting upon these correct state value function or state values. That's pretty important. So basically, using this technique and also the technique we talked about called policy iteration, we use either one. We can actually solve an MDP. So if we were to define a problem, get the transition probabilities and everything that we need for an MDP that we've been discussing since the first few weeks, we can actually solve an MDP and create a policy that makes allows us to navigate through this environment and get to our optimal return. So that's the value of value iteration. And of course, we're going into more examples where we've already talked about Monte Carlo last class, and there will be someone on the midterm exam as well for reviewing, and I think we'll also likely have some more review for that as well if you have any questions. And yeah, so that really covers the video, and of course please ask on Piazza, and we're allowing submissions for the homework corrections. So check my previous Piazza post on that, and I hope this video helped you.